Hello everyone. In the last video, we have started with a new subtopic, that is variational problems with moving boundaries. Okay, and we have already seen what are these variational problems with moving boundaries. All this time, whatever we had studied, in that we were dealing with the functionals which look of this type, but the endpoints of the extremal that we are looking for, they were fixed. Okay, and our class of admissible curves was looking something of this form. That means all the curves passing through these two fixed points. Okay, now in variational problems with moving boundaries, we have seen that there are two curves and point B and point A. So basically I'm talking about the two endpoints of the extremal. Okay, they are allowed to move on this curve. Let us suppose say xi of x, and this point is allowed to move on the curve say phi of x. Okay, and this is our point x naught, and this is the point x1. Okay, so we look, and this is the extremal curve. So this endpoint is allowed to move on this curve. This endpoint b is allowed to move on the curve phi of x, and these are the variational problems with moving boundaries. We have also noted down the steps to solve a variational problem with moving boundaries. And in those steps, in step 3, we have written something called as the transversality condition. Okay, so today we will see how do we get that transversality condition. The procedure to get this transversality condition, it is the derivation. So the proof of the theorem that we will not see in full detail, but I will give you all an idea about how we get that transversality condition. Okay, we will be focusing more on the problems. So to start with, let us suppose say I am dealing with a variational problem with moving boundaries. Okay, so if on a curve y equal to y of x, an extremum is attained in a problem with moving boundaries, then moving boundaries means what? The endpoints are allowed to move. Okay, and y equal to y of x is an extremal, is the curve on which the extremum is attained by a functional. Okay, then we have seen that it will certainly attain the extremum on a restricted class of curves with fixed boundary points. Okay, I think I have already explained this in the last video, that if we say y equal to y of x is a curve on which the extremum is attained in a moving boundary problem, then the extremum will also be attained also on the problem with fixed boundaries. Okay, and therefore the basic condition for attaining an extremum in a problem with fixed boundary points. And what is that necessary condition? It is that the curve should satisfy the Euler-Lagrange differential equation. Okay, so this condition must also be satisfied by this y of x. What is this y of x? It is a curve on which the extremum is attained in a moving boundary problem. And because of the reason that I already said, this curve, it should also satisfy the Euler-Lagrange differential equation. Okay. Therefore, the curves y equal to y of x on which the extremum is attained by the functional this. In a moving boundary problem, must be the solution of Euler-Lagrange differential equation, which is given by Fy minus d by dx of Fy dash. Okay, I think all this I have already said it in the previous video. Okay, how we get that this is satisfying this Euler-Lagrange differential equation. And therefore what we say, this curve y equal to y of x, it must be a extremal. It must be a extremal. Now, the main thing here is, why are we looking for some conditions, or why are we searching the conditions? That is because for this problem, we are not given the points x0, y0 and x1, y1. That means the two boundary points. That means the initial conditions. Because when we get the solution of this function Euler-Lagrange differential equation, it is of the form fx comma c1 and c2. It has the c1 and c2, which are the arbitrary constants. All this time what was happening was, because of the two initial conditions that are given, we could determine the c1 and c2. But now it is that these 2 points, or maybe one of the point, will not be fixed. It will be moving on a given curve. Okay, and therefore we need some additional conditions, which are called as the transversality condition, to determine the constants c1 and c2. Okay, therefore the missing condition for determination of the arbitrary constants of the general solution of Euler-Lagrange differential equation have to be obtained from the basic necessary condition for an extremum, which is the vanishing of variation delta v. Okay, and we need some conditions to determine the c1 and c2. So we will find out these conditions by using the fact that if on a curve y equal to y of x, the extremum is attained, then delta v is equal to 0. Okay, that means the variation is 0. So we will use this fact to derive the conditions which will help us to determine the constants c1 and c2. Now let us consider the case where one of the point from among these points A and B, okay, one of the point is fixed. Let us suppose take this point A is fixed. That means x naught comma y naught is fixed. It is not moving. Okay, and the other boundary point, that means this point B, let's call it as point x1 comma y1. This point x1 comma y1, it can move. Okay, this point can move on this curve, and when it moves, it will pass through all such points, x1 plus delta x1, y1 plus delta y1. Okay, so whatever is the increment, when this point is moving, definitely it is clear that there will be a change in the x coordinate as well as in the y coordinate. Okay, so we are denoting it by this. So this point is allowed to pass through the point x1 plus delta x1 and y1 plus delta y1. Okay. Now what we will do is, since we know that this point is fixed, now our work is reduced. We will have to look at all the extremals. One point is fixed, no? So whatever is the extremal, that will certainly pass through this point A. And what we want to find out the curve such that the extremum is attained on that curve. Okay, so from this x c1 c2, it is clear that one of the constant can be determined. Okay, because this one point is fixed, we know the one initial condition, but the second one, it cannot be determined. And therefore what we will be doing is, the extremal passing through the point x naught y naught, okay, they will form a pencil of extremals form a pencil of extremals which look like y equal to y of x comma c, and the functional v of and this functional we are evaluating this v only on the curves of this type y x comma c1. Okay, so this functional on the curves of this pencil, on the curves of this pencil. So this is a pencil. I'll show you all how it becomes a pencil and why it's called as a pencil of extremes. Okay, so if we evaluate this v only on the curves of this pencil, then this functional is reduced to a function of x1 and c1. Okay, then this functional is reduced to a function of x1 and c1. So what happens is we will look at only such extremals. Okay, so let us suppose say 1 is the point x1 comma y1. Okay, so this is the point x1 comma y1. Then this will be x1 plus delta x1 comma y1 plus delta y1. Okay, so it is that point, and only the second point x1 y1 is allowed to move, and this first point it is remaining the fixed one. Okay, so therefore Euler Lagrange equation, sorry, the solution of Euler Lagrange differential equation, which was looking like this: f x c1 c2. Okay, because one of the point is fixed, now this will be of the form, and this is nothing but y, this, because we get y of x equal to something in terms of c1 c2 and x. Okay, so now because the one point is fixed, then this will be of the form y equal to y of x comma c1. It will be a function of x and c1. Okay, now what we do is we look at all these extremes, and if you see, my figure is not the diagram that I have drawn is not very perfect, but if you draw it properly, it looks exactly like a shape of a pencil, and therefore it is called as pencil of extremals. Okay, now we evaluate this v only on these curves. Okay, and then from among these curves, on which curve the extremum is attained by a functional, that we will have to find out. Now, if the curves of the pencil y equal to y x comma c1 in the neighborhood of extremal under consideration do not intersect, then what we can do is we can say that this v y x comma c1 is a function of x1 and c1. Okay, so what happens is if these are the extremals which do not intersect each other, then if I tell you what is the end point, then easily you can locate which is that extremal curve. Okay, so because if there is intersection between the curves, no, then what will happen is for one point there may be two extremals. Okay, if there is intersection between this curve, like this, suppose. Okay, there is one more curve, and if I tell you which is this point, which is this end point, then it is not easy to say, or it is not possible to say which is the curve on which the extremum is attained. Okay, that means it cannot be uniquely determined. But if we say that these there is no intersection between these curves, whatever I had drawn previously, except this one, okay, that means there is no intersection between those curves. Under that condition, if I tell you what is the second endpoint, then you can easily tell me which one is that extreme. That means, suppose if I say this is the second endpoint of the extremal, then easily immediately you can say that this is the curve on which the extremum is attained. Okay, therefore what is said here is, if the curves of this pencil, okay, in the neighborhood of y equal to yx comma c1, sorry, not y equal, the on the extremal under consideration do not intersect, if these curves they do not intersect, then this v y x comma c1 can be taken as a function of x1 and y1. Okay, I think I said x1 and c1. Yes, it's like, because when I tell you the second point, what am I telling you all? I am telling you all what is x1 and what is y1. Okay, so if there is no intersection between the curves of this pencil, then we can say that this functional v y x comma c1 is a function of x1 and y1, because specifying the values of x1 and y1 will determine the curve or the extremal of the pencil. Okay, and thus the value of the extremal. How the value of the extremal? Because once you know which is that curve, and so what we have to do is we have to substitute it in this functional v, and then we will get what is the value of that function. Okay, so initially what we do is, let us determine the variation of the functional v y of x comma c1 when the boundary point moves from x1 y1 to x1 plus delta x1 y1 plus delta y1. Okay, so if the second boundary point is moving from this to this, then what is the variation in the function? Okay, so that is given by delta v is given by integral from, okay, well, let's first write it in this form. So y of x plus, so this will be integral from x naught to x1 plus delta x1. Okay, delta x1. So on left hand side the point is x naught, and on the RHS on the other end point is x1 and y1. Okay, but that x1 y1 is moving from x1 y1 to x1 plus delta x1 comma y1 plus delta y1. So initially we are calculating this curve, that is f of x y plus delta y comma y dash plus delta y dash dx minus integral from x naught to x1 f of x y y dash dx. Okay, now this first term here we can split and write it as x naught to x1 plus integral from x1 to x1 plus delta x1. Okay, so this will be splitted into two terms, and then from among those two terms the first term, that is integral from x naught to x1, we can combine it with this. Okay, so by using all that I will write here this will be f of x comma y plus delta y comma y dash plus delta y dash minus f of x y y dash into dx plus integral from x1 to x1 plus delta x1 f of x y plus delta y comma y dash plus delta y dash dx. Then what we do is by using the mean value theorem we write this term, okay, this second term to be equal to capital F at the point x equal to x1 plus theta times delta x1, okay, into delta of x1. That means this term is equal to this quantity. Okay, so you see here this theta, it will lie between 0 and 1. Okay, so it is like x1 plus theta delta x1. This is the point that is lying between x1 and x1 plus delta x1. Okay, so evaluating f at that point into the length of this interval. Okay, because what does the mean value theorem says? Whatever is here, this quantity, the derivative of that, so that we will get f at the point c. C is the point between the interval. Okay, so that point c is written in this form: x1 plus theta times delta x1 into the length of the interval, that is b minus a. So b minus a will be delta x1. Okay, so this second term over here is written in this form by using the mean value theorem. Okay, and there is, because capital F, it is continuous, what we can do is this capital F, it can be written as this capital F, it can be written as, because it is into delta x1. Okay, so it can be written as f evaluated at x equal to x1 plus some quantity epsilon. Okay, this by the continuity of this f. Okay, I think this is the very standard form of this thing, because what does the continuity tell us? F of x minus f of y is strictly less than epsilon. Okay, so that, and what are these 2 points? These 2 points, they are the closed lying ones. Okay, so for the closed lying ones, what you can do is there is a very little error between them, between the in the function value at those 2 points. Okay, and by using that, what we can do is at this point this capital F can be written as f at x equal to x1 plus some epsilon quantity. Okay, where this epsilon, it will be very small and it goes to 0 as this delta x1 goes to 0 and the delta y2 goes to 0. Okay, because as this delta x1 and delta y1 are going to 0, what will this point get reduced to? this point will get reduced to the point x1 comma y1, okay, and which is nothing but exactly this. So this is capital F at x, y, y dash at the point x equal to x1. That is what we will get if this delta x1 and delta y2 goes to, sorry, delta x1 and delta y1, if these two go to 0. Okay. And then by using the Taylor's theorem and some other facts, we come to the conclusion that this delta v, it is equal to integral from x naught to x1 fy minus dy dx fy dash into delta y dx plus fy dash into delta y from x naught to x1. Okay, and then in this expression you can clearly see here this first part, it is nothing but the Euler Lagrange differential equation. Okay, and we have said that whatever is a curve on which the extremal is attained in a moving boundary problem, that curve is an extremal. That means it is a solution of Euler Lagrange differential equation, and hence this term, it is going to 0. Okay, so this will give us that this delta v is equal to, and what happens is this delta y at the point x naught, okay, it goes to 0 because the point x naught comma y naught is a fixed point. So whatever extremals we are considering, for those at the point x naught, all will take the value y naught. Okay, and therefore the variation at that point will be going to 0, and hence we are left with f y dash at x equal to x1 into delta y at x equal to x1, because at the point x naught this delta y goes to 0, and hence that second term is vanishing. Okay, so we will be left with f y dash into delta y at the point x equal to x1 plus yes, here I, yeah, that should be this term, f at the point x equal to x1 into delta x1. Okay, so this will give us, now see here, this delta y, when we say at the point x equal to x1, that means actually it is not equal to the delta y at the point x equal to x1, that is delta y1. Okay, by this term, that is delta of y evaluated at delta of y at x equal to x1, it is the increment of the ordinate, meaning ordinate means we have 2 points, no? So this point is called as the ordinate. This, it will denote the increment of the ordinate at the point x equal to x1, okay, when the extremal is joining the points this to x1 y1, this is one extremal, and x0 y0 to x1 plus delta x1 comma y1 plus delta y1, okay. So what this term denotes is the increment of the ordinate at the point x equal to x1 when passing from the extremal joining the points x0 y0 and x1 y1 to the point joining x naught y naught and x1 plus delta x1 comma y1 plus delta y1, okay. So you see that, see here, this is one extremal and this is the another extremal. So when the extremal is passing from here to here, that means from this to this, okay, sorry, there should be no intersection. So from here like this to here, when this is happening, at that time what is the change in the ordinate, that is denoted by this quantity, okay. And it is not just this delta y1, okay, that means this. What does this denote? This denotes the increment of the ordinate point when the point is displaced from x1 y1 to x1 plus delta x1 comma y1 plus delta y1, okay. So what this quantity denotes is, if the point is shifted from this point to this point to this point, then what is the change in the ordinate, that means the second coordinate, that is given by this quantity delta y1. But what we are looking at is delta y at x equal to x1, and the meaning of that is this. So when the extremal joining this point and this point, it is moving from here to here, that means the extremal joining this point to this point, that time what is the change in the ordinate, okay. So that is given by this term, and it can be seen that, meaning we can show this actually, x equal to x1. So this quantity is equal to, approximately equal to delta y1 minus y dash at x1 into delta x1, okay. And from all these facts what we get is delta v is equal to f minus y dash into fy dash delta x1 plus f y dash at the point x equal to x1 into delta y1. From all the previous procedure, whatever I have said, we get such a equation, okay. Now, if suppose this delta x1 and delta y1, they are varying, they are changing independently, then the necessary condition for the extremum is, if suppose this and this, they are independent, then what will happen? If I take this quantity, we are looking at extremum, okay. So this delta v will be equal to 0. So what will that imply? 0 is equal to this equation, okay. And we have said that suppose this delta x1 and delta y1, they are varying independently. What does that tell us? That means the coefficients should be equal to 0. That means fy minus y dash, sorry, f minus y dash into f y dash at the point x equal to x1 equal to 0 and f y dash at the point x equal to x1 is equal to 0. Okay, but if they are not varying independently, not varying independently, then what will happen is we will get that this delta y1, whatever is there here, delta y1, it is phi dash at x1 into delta x1. Okay, because you see here we had taken that the point x1 y1 is moving on the curve y equal to phi of x. Okay, so if suppose these points they are not moving independently and they are uh, if suppose this moves in this direction by some quantity A, then depending on that there will be a variation in the uh, y coordinate. Okay, it is not like x1 the x coordinate will move as it want and then the y coordinate will move as it want. Okay, so depending on how this point is moving, the variation in this point will be determined. Okay, so if that is happening, that means they are not varying independently, then delta y1 will be equal to this, and if you substitute this in this equation, then what we will get is delta v is equal to, so this will be delta x1 capital F minus y dash f y dash at the point x equal to x1 into delta x1 plus f y dash at the point x equal to x1 y dash is x1 into delta x1, and this will give, and we combine the two terms, f x1 plus this phi dash minus y dash into f of y dash, and this whole thing evaluated at the point x equal to x1 into delta x1 equal to 0. Okay, because this delta x1 is varying arbitrarily, what we will get is this term on the LHS. Okay, this is equal to 0. Okay, and this gives us a condition at the free boundary point. Free boundary point means which point? It is this point x1 comma y1. Okay, so it is this condition that should be satisfied at this point. The condition is f plus phi dash minus y dash into fy dash at the point x equal to x1. Okay, and therefore the condition is this equal to evaluated at f plus phi dash minus y dash fy dash at x equal to x1 equal to 0, and this at the point x1 it's equal to y1, because we have said that the delta x1 and delta y1 they are not varying independently. And how they are, meaning why does that happen? Because the point is moving on a curve y equal to phi of x. Okay, and therefore the point x1 y1 it will lie on the curve phi of x. Okay, and this condition is called as the transversality condition. Now, also notice that if suppose the point x naught y1 y naught is also not fixed and it is also moving on some curve y equal to xi of x, then we can come to a similar type of transversality condition in that case as well. Okay, and then it is this transversality condition that should be satisfied by this point. Okay, so then we will have to deal with all these two transversality conditions, and then here it will be xi at x naught is equal to y naught, and these conditions in order to find out what is the point x naught y naught, then what is the point x1 y1, and the constants c1 and c2. So if you see the steps that we have already noted down to solve a a variational problem with moving boundaries, you will see that in the third step we have given these two transversality conditions. Okay, so if only one point is fixed and the other point is moving, then we will get only one transversality condition. But if both the points are allowed to move on the curve xi of x and phi of x respectively, then we will have to determine all these values by making use of the transversality condition and the solution of Euler-Lagrange differential equation. Okay, the main thing here was we were looking at only the curves which are belonging to that pencil of extremals. Okay, we had fixed the one point and then we allowed this point to move.